Reservations in two-way slabs by means of yield lines. This video will deal with cases 16 to 20, and it's about a slab with three sides fixed and one side freely supported. We will talk about case 19, and case 19 and 20 are special because the yield lines do not follow the 30, 45, 60 rule. They follow the rule, what is called attracting yield lines. It means that every corner, the corners of the reservation is attracting the yield line, independent of the angle that it will make. And there are two cases. First, to start with, I take a centric hole. So that means that the hole is in the center of the slab. And later on, we will finalize it with case 20, where the hole is not centric. So case 19, it's about a centric hole tracking yield lines. It's a one-way slab, so we know this condition, which is B must be between A and 2A. We have reservation it, D1 by D2. And this reservation has a position in the center of the slab, so it means left and right. It's D4 and it's equal. Top and bottom, it's D3 and it's equal. So the maximum hole size, of course, must obey this rule. And because of the symmetry, you have this equation. Simple, it's just the summation D3, D1 plus D3 will be equal to A, and D4 plus D4 plus D2 will be equal to B. Yield lines, negative bending moments, we have a yield line according to B. We have a yield line according to A and one yield line according to B. And then we take the point where the rotation axis cross and we draw a yield line right to the left top corner of the reservation. So we do not bother about the angle. It's attracting yield lines. So in the four corners, we have those yield lines. And now we can study this case 19. The set conditions, we can now visualize how those reservations look like. The black line here is the fixed end and the other is the simply supported. This is the centric hole attracting yield lines. It can be a horizontal reservation, it can be square like this and large, or it can be a vertical. First thing, we must note that if this reservation is approaching the edge, then you will have two yield lines, which is there on the support, and then the one just attracting the corner. So this is not very realistic as a yield line. So we must be careful by using attracting yield lines that the reservation is not too close to the edge of the slab. We have now different parameters, and we can calculate the work done by the external forces, which is easy. The triangles are E4 times D3, and it is 4 times, and the mean deflection is delta over 3. And for the orange parts, it's D2 times D3, 2 times, and D4 times D1, 2 times, and the mean deflection is delta over 2. We will use the dimensionless parameters by dividing by the smaller size of the slab. The work done by the internal forces is this yield line of the negative bending moment, which is B, divided by the angle of rotation, which is delta divided by D3. We have here this yield line and this yield line, so that's where you have 2 B over D3. This yield line gives you A over D4, and then what's left are the four corners. The four corners is this yield line projected to this axis of rotation. So it is the length of it D4 divided by D3. And on the other side, it is D3, this one divided by D4, because we are projecting on this axis of rotation. And then we do it for the other side. It's the same thing, and it's 4 times 2 plus 2 plus 2 plus 2. We fill in the parameters, and then from d is equal to e, we calculate m, and then you arrive at this formula, which is, of course, a function of alpha, alpha 1, and alpha 2. The definition of the bearing capacity, it's 100 times maximum bending moment without the hole divided by the maximum bending moment with the hole. The maximum bending moment without the hole, we've seen that in the previous videos. It's equal to this formula. And the bearing capacity is then can be written as this because it's just 100 times m0 divided by m. You notice immediately that in this position of the formula, alpha must always be bigger than alpha 2, which is logic. That means B must be bigger than D2. That's logic. And here the same, alpha must be bigger than D1. You can see it in the formula. Now, let's visualize it. Suppose this is a reservation and a slab with alpha 1.5 and alpha 1.5. So it means that this is half of this length, and this length is 1.5 times this length. And alpha 2 is 0.1, so that's the width of the reservation. You can use this formula, you can calculate, and you see that making a reservation like that does not lead to loss of bearing capacity. So that's nice to see. Now let's look at in more general. The x-axis is alpha from 1 to 2. The y-axis is the bearing capacity. But we have now 3 variables. So that's alpha, that's the first variable. Okay, that's fine. But we have d1 and d2 as a variable. So we take here d1, it is the smallest dimension of the reservation as 0.2. And this is we vary alpha 2 from 0.2, from 0.2, the red one, up till this 0.8. See what is happening. And we see that there is only a small area where the bearing capacity is not 100%, and all the others it's above 100%. So that's a good sign. Now let's take an example. Alpha is 1.6. It looks like that. And for alpha 1.6, we see alpha 1.6. We see that for square of 0.2a and 0.2a, we have this point, and this is 104 bearing capacity. For the width of the reservation equal to 0.4, we have in the blue dotted curve, and we are at 101. And for the black curve, the alpha 2 is 0.6, so it's larger reservation. So the bearing capacity is 99%. And at last, we have 0.8 for alpha 2, and this is 100%. So this is what's happening here. Now we'll have a closer look at this interesting area where the bearing capacity is smaller than 100%. Again, alpha 1 is taken as a constant just to study one case, not all cases, but to show how it goes. And alpha 2 from 0.2 to 0.8. Then you can, for instance, see for alpha 1.6, we have here 104 as bearing capacity. This we have 101 as bearing capacity, and this point we have 99% as bearing capacity. So now from this curve, you can visualize what type of reservation is interesting for the slab. And this is the fourth one, which is 100%. Now, we can now do the same, but we will fix the bearing capacity for square slabs. Alpha is 1. We fix alpha. The variable is alpha 2 from 0 to 0.6, and we vary alpha 1 from 0 to 0.6. And then you got those curves. Again, as a demonstration, This is for alpha is 1, so it's a square, and 0.2 is D1, and D2 is 0.4. So this is twice this size. So alpha is 1, alpha 2 between those two limits. And it gives you a bearing capacity of 105. Again, now we can do the study for alpha equals 1.5 and draw the different curves. And again, we see for alpha equals 1.5, which is the green curve, you have this range. And it's no problem at all. The green curve is always bigger than 100%. We take one particular case, alpha is 1.5, then we take the red curve, which means that the size of alpha 1 is 0.1 times A. So there's a smallest reservation with alpha 2 ranging from 0 to 1.1, from 0 to 1.1. And we see on this, the bearing capacity is 100%. And on this, so on this small hole, it's 100%. Smaller than that, you will increase the bearing capacity. Bigger than that, you decrease the bearing capacity until you reach this size, and then you increase the bearing capacity again. That's a way of using those graphs. Now, in general, looking at a graph of alpha 2 ranging from 0.6 and alpha going from 1 to 1.5, because we've seen on the previous slides that when alpha is bigger than 1.5, there's no problem with bearing capacity. So that's why we have limited us to alpha equals 1.5. You see this area. I make this area larger, and then you will see here that in this area, this is the one which is interesting for us. It means that for alpha 1 equals 0.2, that for alpha 2, the other dimension of the reservation going from 0 to 0.6, that you must avoid all those values which are here indicated in the pink. So for each value of alpha, you will find the corresponding alpha 2 that you may or may not use. Let's take square hole in a square slab. So D1 is equal to D2, and alpha 1 is 0.6. This is 0.6 times A. Or alpha 1 must be smaller than 0.6 because otherwise you have no realistic yield line. So you must have here some body of the slab, otherwise attracting yield lines you cannot use. So that's why alpha 1 is smaller than 0.6. Filling into this parameter, you will have the maximum bending moment as a function of alpha 1. We can make a graph, alpha 1 from 0 to 0.6, and the bearing capacity on the y-axis. Written in a formula, it's equal to this. This is the red curve. And we see here the maximum. You can easily calculate the maximum of this formula. You will see that the maximum is at alpha 1 equals to 0.11, and it is 97. Maximum, I mean a minimum, a maximum of loss, but it's a minimum value. The bearing capacity for alpha 1 0 would in fact be 100%. And for 0.22, it's also 100%, which is this point. And for alpha 0.6, on this side is 187%. So the bearing capacity is smaller than 1 for a square hole in a square slab, as long as alpha 1, the size, is smaller than 0 and 0.22. So it means that you have to avoid making holes in square slabs smaller than 1/4 of the slab dimension. So you should think that the bigger the reservation is, the smaller the bearing capacity, which is not necessarily the case. Here, for square slab, centric square slab, the smaller you make the hole, the reservation, the larger your loss in bearing capacity becomes.